So these our team members consists of 4 people, which are Aina Nasira, Nur Jiha, Alia Maisara, and Nabiha.
Now, let's move on into the core of our topic, which is N-type and P-type semiconductors. Before we look at the differences, we first need to understand why we study doped semiconductors in the first place. While pure or eccentric semiconductors like silicon are fascinating, they actually have very limited conductivity on their own. To make them useful for modern electronics, we use a process called doping. This allows us to precisely control and enhance their electrical properties. Broadly speaking, semiconductors fall into 2 categories, which is first, intrinsic semiconductors. These are pure materials with naturally low conductivity. Second is the extrinsic semiconductors, which is these are semiconductors whose conductivity has been significantly increased through the addition of impurities, where the process we call doping. So, how does doping change the material? It depends on what we add. This leads us to the 2 main types of extrinsic semiconductors, which are P-type and N-type. For P-type, the semiconductor is doped to create extra holes. Think of these holes as positive charge carriers. That's why we call it P-type. The P stands for positive, whilst N-type, in this case, the material is doped to have extra electrons. Since electrons carry a negative charge, we call this N-type, where the N stands for negative.
Next is the topic overview. So, pure semiconductors have limited electrical conductivity at room temperature. Their electrical properties can be modified by introducing control impurities, a process known as doping. So, this produce 2 forms of extrinsic semiconductor, which are N-type and P-type. For N-type, semiconductor are formed by adding donor impurities that increase the number of free electrons, making the electron a majority charge carrier. While for the P-type are formed by adding acceptor impurities that creates hole as majority charge carrier.
Next, I will explain about background and history. So, what is semiconductor? Semiconductor is material with electrical conductivity between conductors and insulator. So, commonly made from silicon. So, early studies in the early 20th century show that pure semiconductors had limited conductivity. So, a major breakthrough occurred when scientists discovered doping. Doping is a process of adding impurities to control electrical properties. So this leads to the development of P-type and N-type semiconductor. So the most important milestone was the invention of the transistor in 1947 at Bell Laboratories, which marked the beginning of modern electronics.
So, what are the difference of P-type and N-type? For P-type, the material is trivalent impurity, meanwhile N-type is the pentavalent impurity. For P-type, the role of doping material is acceptor atoms, while N-type is donor atoms. For majority carriers, for P-type is holes and N-type is electron. For minority, P-type is electrons and N-type is holes. So now let's move into their applications. So one of them is diodes, to control the direction of electric current in circuits. Next is sensor, which detect light, heat, pressure, or motion. Next is LEDs, which produce light efficiently using semiconductor materials. Next is transistor, used for switching and amplifying electrical signals. So the other one is solar panels, which convert sunlight into electrical energy. Lastly is power supplies, which regulate and convert electrical power.
So now that we understand the basic concepts of doping, let's look at the specific materials and elements used to create these semiconductors. The type of semiconductor we get depends entirely on the chemical properties of the dopant we add to the pure material. First, let's look at the N-type semiconductors. To create this, we use pentavalent atoms which have 5 valence electrons. When these are added to a semiconductor like silicon, they provide extra electrons which act as charge carriers. These elements are known as common donor dopants because they donate that extra electron to the structure. Common examples include phosphorus, arsenic, antimony, and bismuth. In practice, we see this when silicon is doped with phosphorus or arsenic, or when germanium is doped with antimony. On the other side, we have p-type semiconductors. These are created using trivalent atoms which only have 3 valence electrons. This shortage of electrons creates extra holes or positive charge carriers. We call these common accepted dopants because they are looking to accept an electron to fill that hole. Typical elements used here are boron, aluminium, gallium, and indium. Examples of these materials include silicon doped with boron or gallium and germanium doped with indium.
For advances and innovation, firstly, we could have to improve the doping control as the modern technology allows us to control the amount of impurities more precisely. This helps to form a clear N-type and P-type semiconductor, improving charge flow and device performance. Second, miniaturization of PN junction device. PN junction are now made smaller with advanced fabrication method. This smaller device could work faster and use less power more efficiently. And lastly is the nanostructure semiconductor. So by using nanomaterial, this could help to improve how electron and the hole move. This also could help to increase electrical conductivity and improve device performance.
Next, we proceed to advantages and benefit of p-type and n-type semiconductor compared to pure semiconductor. So first, conductivity. Pure semiconductors have lower conductivity because they don't have any excess charge carrier, while n-type and p-type semiconductor, through the process of doping, they have a higher and more efficient conductivity. N-type has excess free electrons, while p-type has excess hole. So this allow current to flow more easily. Next, for charge control. Charge control in semiconductor is limited. However, in n-type and p-type semiconductor, we have precise control via doping and resulting in better device performance. So last, for device use, pure semiconductor have limited use. Conversely, the unique features of N-type and P-type allow for the formation of p-n junction. P-n junction is the foundation of diode, transistor, and integrated circuit. So this is the key advantage that enable control current flow in electronic device.
So, what are the limitations or challenges of N-type and P-type? For N-type, they are dependent on donor impurities. So, if the dopant concentration is too low, the conductivity remains limited. But if they're too high, crystal lattice distortion may occur. So, it reduces material stability. The next one is temperature sensitivity. At a high temperature, excessive thermal excitation can reduce control over conductivity. This makes it less reliable under extreme thermal conditions. For P-type, it is dependent on acceptor impurities. So when there is insufficient doping, it creates few holes that result to low conductivity. Meanwhile, when there is excessive doping, it creates structural defects in the crystal lattice. Next is temperature effect on hole concentration. At elevated temperature, unwanted electron-hole recombination may occur, reducing effective charge carriers.
Next is the future trends. First, new semiconductor material. So the scientists are currently exploring new material to replace the silicon. This material could help to perform better, especially at high temperature. The second is integration with nanotechnology. So at the nanoscale, we can control electron and hole better. So this could help to improve the electrical properties and device efficiency. The third is higher energy efficiency. So in the future, semiconductor will be designed to reduce energy loss. This helps devices like solar cell and LED to work more efficiently. Lastly is further miniaturization. So the N-type and P-type will become even smaller as smaller devices work faster and use less power.
To conclude, we've seen how doping is the key to transforming pure semiconductors into high-performing N-type or P-type materials. The main takeaway is the difference in their charge carriers, which is N-type relies on extra electrons while P-type uses holes as majority carriers. By combining these two types, we create the diodes and transistors that power all modern electronics. Understanding these materials is essential because they truly are the foundation of our entire digital world. Thank you for listening.